This lecture covers Chapter 5, Membrane Dynamics, in your textbook. You should also refer to the Chapter 5 study guide and the associated questions that you'll be turning in to know what material you're responsible for knowing that will be covered on the exam. So let's begin this discussion with a hypothetical question. Let's say a man walks into an ER and he's like this. Perhaps another one walks in and they're like this. Or a third walks in and they're having this. What do we do and why? Today's lecture, we're going to focus on the cellular mechanics of how we fix and mitigate these problems. Our body is constantly striving to balance the solute concentration and its water concentration. And if I asked you what is the most important molecule in the human body, if you thought about that, hopefully you would come up with this notion that water is the most important molecule in the body. It's the most important molecule because it makes up, in men, as much as 65% of their body weight when they're infants, and women, it's a little bit less as we start to get older. So you'll notice that when we're younger, water makes up a larger component of our body. So you start to get older, it becomes less. In men, the average at let's say a 40-year-old 55%, and a woman it's a little bit lower than 50%, but it makes up the majority of our body. And as such, osmotic equilibrium is important. That's the concentration. So this little symbol right here, when we see these brackets and a word inside that means the concentration of fluid are equal on both sides of a cell's membrane. So we can break the body into compartments. We have a compartment that we call the ICF, or the intracellular fluid. This would be the fluid inside a cell. And we have the volume that makes up the ECF, or the extracellular fluid, the fluid that exists outside the cell. That fluid can be found in our blood plasma or in the interstitial fluid that just is bathing our cells. The ICF makes up roughly 2/3 of our water volume in the body. ECF is 1/3. And what separates these two components is going to be the cell membrane. Now, just because we have an osmotic equilibrium on both sides of the cell membrane, does that mean we have equal amounts of water per se, and does it mean that the solutes on either side are the same? And the answer to both of those are no. Obviously here it's 1/3 for water is found in the cell, 2/3 are found outside of the cell. The reason why the water volumes aren't necessarily the same is because we have different solutes that are found within that. So osmotic equilibrium, it's the concentration of fluid as a function of the number of particles per liter. That's osmolarity. Number of particles per liter is our osmolarity. And when we look at our different fluid, what we'll find is we have very different solute concentrations that are found inside and outside the cell. So inside the cell, for example, potassium is the largest, has the highest solute concentration, that ion concentration, followed by proteins. Okay, outside in the interstitial fluid, we don't have very many proteins. In the plasma, yes, we do have some proteins, but outside, the ions that make up most of that solute concentration are going to be sodium and chloride. So salt outside the cell, potassium inside the cell. We call this difference in solute concentration a chemical disequilibrium. Okay, so our chemical concentrations are in disequilibrium, and that creates an electrical disequilibrium that we'll talk about to a great extent when we talk about nerves and muscles. Let's talk about osmosis. Osmosis is the movement of water across the membrane in response to its solute concentration. So we're are going to be moving water from areas of low concentration of solutes to areas of higher concentration, because ultimately on two sides of a membrane we want osmolarity to be equal. So how do we measure osmosis? There's a couple of ways. We could use osmotic pressure, osmolarity, or osmolality. These are all slightly different, but for all intents and purposes, for the most part in this class, other when we get into gas dynamics, we'll talk about osmolarity. Okay, so number of osmoles, or number of particles per liter. And you'll see here's a selectively permeable membrane. We have more solutes on this side, so glucose molecules are higher than on this side, and so osmosis would dictate that if we were to calculate the osmolarities here, so the number of solutes per liter, and I'm going to just write something out. Let's say on this side we have 1, 2, 3, 4, 5, 6, 7. So let's say we're 7 osmoles per liter. And over here, if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 osmoles, okay? These need to be equal. And so what will happen is we will move, we can't change, in this case, the solutes. They can't move across this membrane since it's selectively permeable. So glucose can't move across. We can't have diffusion. So we have to have osmosis in which water moves. And so we're going to change the bottom part of this equation, the amount of liters that are found on this side. In order to get this number bigger, we want to decrease this number. So what we see is water moves to the side where we have a higher concentration. That's going to increase the denominator on this side, so make the volume larger, which will decrease our osmolarity, and we'll meet in the end in which we have an equal osmolarity. That's osmosis. How do we measure dehydration, or the water loss in an individual? Well, we can do that by basically looking at what is the weight loss or fluid loss in an individual, and 1 liter of fluid loss is equal to 1 kilogram. So if somebody's been out in the desert for a long time, you knew how much they weighed before they went into the desert, you find them a couple days later, you take their weight, you could calculate essentially how much water lost and how dehydrated they are. Now, there is another concept that is often put with osmosis, and that concept is known as tonicity. So when we compare two solutions that have osmolarities, we can compare those as far as their osmolarity is concerned, and they're either isomotic, meaning that the number of solutes per particles per unit volume are equal. So at the end of this, here, these two fluids are now isomotic. They have the same osmolarity. Or, I should be showing it right here, right? The same osmolarity. In the beginning, though, this solution had less, right, particles per liter. Therefore, it is hypoosmotic, and this was hyperosmotic. So, hyper meaning you have a higher concentration than the other, hypo meaning you have a lower concentration of solutes than another, and iso meaning they're the same. That's when we're comparing osmolarities. But tonicity, now this describes a solution and how it will affect a cell's volume. And we can be either isotonic, hypotonic, or hypertonic. And again, if we look at what happens in an isotonic solution, so we have roughly the same solute concentration outside the cell versus inside, we don't have any water exchange. There's no osmosis, so the cell stays the same size. If we have a hypotonic solution, however, in which there are less solutes outside the cell than in, that water is going to want to diffuse into the cell in order to balance the osmolarities. And in this case, our cell is going to either lyse, or in the case of a plant cell that has a cell wall, it becomes turgid. It's going to swell. The inverse of that would be if we have a hypertonic solution where there's more solutes outside the cell than in, and so water is going to want to move out. and that's going to cause the cell to either shrivel, well, sometimes we call it plasmolyzed. So tonicity really talks about the effect water has, or the effect a solution has as water moves in or out of a cell. So can we use osmolarity to predict tonicity? So if a solution is hyperosmotic, does that mean it will also be hypertonic? And that's a really good question. We don't want to necessarily be misled, though, by osmolarity. There is a very specific relationship between osmolarity and tonicity. So we have to ask ourselves, first of all, are all solutes equal in terms of osmolarity and tonicity? For osmolarity, the answer to that question is yes. It's just the number of solutes per liter of water. It doesn't matter what type of solute it is. For tonicity, however, there is a difference. And the difference is tonicity depends on the concentration of what we call non-penetrating solutes. So solutes that can't cross or diffuse across the cell membrane. Because if a solute can move across the cell membrane, then it's going to balance its own concentration out by diffusion, which we'll talk about in a minute. If it can't, however, if its movement is restricted, then the only way the osmolarity can be balanced is by moving the volume of water. So tonicity really depends on the concentration of those non-penetrating solutes. So what that means is if you have a hypoosmotic solution, it's always going to be hypotonic. The reason for that is you just don't have enough solutes outside the cell. Even if they're all non-penetrating, they're still less, and so it's going to be hypotonic. Can it be isotonic? No. Can it be hypertonic? No. However, we can have an isosmotic solution, but if there are solutes in that solution that can penetrate the cell membrane and move into the cell, well, then it's also possible for it to be a hypotonic solution. If all of them are non-penetrating, then it'd be isotonic, and it's not possible for you to somehow become hypertonic, because when we refer to cells, those solutes don't diffuse out of the cell. By very definition, if you have a solute in the cell, it's not going to diffuse out on its own. And finally, if we have a hyperosmotic solution, it's possible, depending on what percentage of the penetrating solutes are able to pass through the cell membrane, as to whether it is hypotonic, isotonic, or hypertonic. Now, this brings us back to that question I posed at the very beginning of the class. How are IV decisions based off these concepts? Well, obviously, depending on where we're having fluid loss, we need to perhaps give a different IV solution. So let's go back to our initial question at the beginning of class. What do we do in these situations? If somebody comes in and they have excessive blood loss, okay, this is fluid from the ECF. They're not necessarily losing any fluid from their cells, though. All right. So in this case, hopefully you administer, a blood transfusion, but you may also be giving an isotonic solution that ensures that we don't have excess. As we give more fluids, those fluids aren't moving into the cell. We want those fluids to be balanced so that the cells don't necessarily expand and explode. We want them to their volumes remain unchanged, but we do want to replace that volume that was lost in the ECF. So we'd give an isotonic IV. In the case of these two examples, someone that has been excessively vomiting, or someone who has diarrhea and they're becoming dehydrated. In this case, as they lose more and more water from their systems, they are also those cells are losing water as well. So it's not just a loss from the ECF per se. It's more of a loss of water from their ICF. So here we're going to give an IV that is perhaps hypotonic. Okay, it has less solutes than what's in the cell, and that's going to then ensure that water moves from the ECF into the cells themselves to replace that water loss that occurred through dehydration. So IV decisions are really based off of tonicities and osmolarities. You may ask yourself, is there ever a time in which somebody would give a hypertonic IV, in which it's pulling fluid from the cells? The answer to that is they are very rarely given, but a case in which you might give this is if you had, let's say, like brain swelling, or probably that'd be the biggest thing, is when we have brain swelling, you're trying to reduce the fluid in some of the cells in the brain. We're trying to bring that stuff out. You could give a hypertonic solution. However, you run the risk of very rapidly pulling water out of cells and therefore like causing damage to the body. And so hypertonic solutions or hypertonic IVs are only administered when there's a doctor present, and they're very, very closely monitored. So we talked about water movement, and we mentioned when we talked about tonicity about how we have that's really dependent upon the non-penetrating particles. So at this point, we really should discuss diffusion. Diffusion is when we have movement of molecules from areas of high concentration to low concentration. And when we have that differential between high and low, what we call that is a chemical gradient. That we have a chemical gradient that we are moving those solutes down. And there's a lot of general properties of diffusion. This is taken from your textbook. It's a table from Chapter 5. This is an excellent table. Make sure you understand and go through this. Okay, what are the general properties of diffusion? First off, it's using kinetic energy found within the molecules themselves, right? There's no energy source needed for diffusion to occur. Those molecules are vibrating and therefore will move on their own. Molecules diffuse from high areas of concentration to low areas of concentration. Diffusion continues until those concentrations come to an equilibrium, so until they're equal. At that point, molecular movement occurs and still continues, but that equilibrium has been reached, so we don't expect things to change. Diffusion is faster when we have higher concentration gradients, right? If we're moving a shorter distance, it's going to be faster. At higher temperatures, we increase the kinetic energy in the molecules. They vibrate faster, so that'll increase diffusion. And if we have a smaller molecule, that will also increase diffusion. Okay. Now, when we have diffusion across a membrane, there's a few other things that come into play that dictate the speed of diffusion. First off is the rate of diffusion through a membrane is faster when these things occur. When the membrane surface area is larger. So the larger the surface area, the more opportunities we have to move things across it, the quicker it will occur. The thinner the membrane also makes sense, right? If we have to move a shorter distance, it's going to occur faster. The concentration gradient is larger. Again, just like, higher to lower concentration, that's going to make it. And finally, if a membrane is more permeable to that molecule. So membrane permeability, how the membrane is made up of, the lipid bilayer, if it is, there can be charges associated with that, and that may make a particular molecule more permeable than another molecule. Speaking to that membrane permeability, what's going to depend on that is the molecule's lipid solubility, so the ability for that molecule to move through the lipid bilayer. The molecule's size, the smaller the size, the more permeable it generally will be. And the type of lipids that make up that membrane. That's what dictates membrane permeability. So make sure you know these things. There could be some multiple choice questions like which of the following will make membrane diffusion quicker, faster, or slower. What kind of molecules can pass through a cell membrane via diffusion? The type of molecules that can pass through are those permeable molecules, a molecule that is able to go through. You can have non-permeables. No. How do molecules come through? Well, if we look at a cell membrane, it's what separates our ICF from our ECF, and it's made up of this lipid bilayer, right? Where we have our lipid molecules, they have a hydrophilic head, meaning they like water, a hydrophobic tail that they orient towards the middle, bilayer, since we have two things, and they make up this fluid mosaic boundary around the cell. Embedded in plasma membranes, we have proteins. So we can have peripheral proteins, we can have integral proteins that kind of spread through, are found on both sides of the lipid bilayer. They bypass it. And we can also have what we call a very particular type of integral protein, ion channels. Ion channels are these little, you can think about it like a tunnel that has a gate, and they allow ions or molecules to move through the membrane if those molecules are permeable, if they can associate with that protein. Our membrane proteins, they have four main functions, and they're not always distinct. Sometimes you have a membrane protein that can do multiple things. One aspect is they could be structural, right, and that they're helping the membrane have its rigidity to hold the cell together. You can have proteins that serve as enzymes for enzymatic reactions and chemical reactions that occur. You can have proteins that serve as receptors that bind to other molecules either outside or inside the cell and are used for signaling and triggering reactions. And then finally, you can have what we call transporters. These are proteins that mediate transport either through what we call facilitated diffusion or active diffusion. And you see, here's our membrane transporters. We can have our carrier proteins, channel proteins. Carrier proteins, the protein binds to it, and then it helps it move across. Channel protein, it's like the gated ones that open it up. We can have what we call open channels or gated channels. Difference between here is whether they're closed at certain times or not. An open channel is always open, gated can be closed. And then what opens those gates could be either mechanically gated, voltage gated, or chemically gated. That's what triggers the gate to open, either something mechanical like pressure, touch, voltage, or a chemical difference. Okay, I just went over this. Again, this is from your book. It does a great job kind of showing that. I'm not going to go through the channel proteins again, but what I want to focus on here is that when we have carrier proteins, so here you can see carrier protein, something will bind to it, and it changes the conformation of that protein to where, first it's perhaps open to the ICF, a molecule binds to it, that changes its conformation, and then it opens to the ECF, and the molecule can dissociate and move out. When we have carrier proteins, they can move solutes in a couple of different ways. We can have what's called uniport carriers, in which it transports only one kind of substrate and it's in one direction. That's uniport. Symport is where we move two or more substances, but again, we move them in the same direction. Okay? And then antiport is where we move substances in opposite directions. So one comes in and the other goes out. The types of diffusion, I mentioned we can have either facilitated or active diffusion. So let's talk about what the difference between those are. Facilitated diffusion is passive. What it means is that there's no energy being put into the system. We're just moving ions from high concentration to low concentration, so down their chemical gradient without the input of any energy source. The example that we'll be utilizing throughout this semester and talking about is our GLUT transporters. There's a number of different GLUT transporters. In this case, we're looking at GLUT4. GLUT4 is the carrier protein that glucose binds to and then uses to move into a cell. So when we have high concentrations of glucose outside of the cell, it will bind to the GLUT4 transporter, and that'll help it move into the cell until we get to an equilibrium inside versus out. Now, you may say, well, if that happens, at some point we're going to get this equilibrium and we're not going to be able to move all the glucose in. Well, there's things that the cell can do. It can convert that glucose once it gets into something different, and then we, again, have a higher concentration outside. So that's what we do. We utilize, like, the Krebs cycle, right, inside the cell, in which we take glucose and we turn it into glycogen, or we put it into glycolysis and utilize it up, right? And once it's converted, again, glucose's concentration is higher, so we can keep bringing it in. So we don't use energy. GLUT4 transporter. And I expect you to be able to know that the GLUT4 transporter utilizes facilitated diffusion. It is also a uniport transporter. Active transport, when compared to facilitated transport, is different in that it requires energy. Like, we need to put energy into the system to help mediate that transport of that solute against its chemical gradient. So we're facilitated, we're moving from high concentrations to low concentrations. In active transport, we're usually moving from low concentrations into something that's already high. So it's like moving it uphill. We're going to need to put in some energy. We're going to need to push. We can break active transport into what we call primary active transport, in which that energy source comes directly from adenosine triphosphate, ATP, and the cleaving of that phosphate bond, the energy released when we take that one of the three phosphates off it and turn it into ADP. That energy can be coupled and utilized to move solutes across against their chemical gradient. The other one is what we call secondary active transport. And now in this case, the energy comes from the potential energy stored in the concentration gradient of another molecule. So we move two molecules at once. One is moving down its concentration gradient, and the other one that's moving against its concentration gradient, it hitchhikes, right? It gets pushed. So the examples that I want you to know from your book, because we'll talk about them this semester, the sodium-potassium pump, sometimes also called sodium-potassium ATPase. This is a primary active transport system. In this system, again, carrier protein, it's going to move in opposite directions. So it's antiport. I know this question on here says, is this uniport, symport, or antiport? I gave you the answer. It's antiport. What happens is we take 3 sodium ions from the ICF and they bind in. Okay, we attach a phosphate. We utilize that energy from ATP. Okay, when that occurs, that's going to change the conformation, and it's going to allow that carrier protein to now open up to the ECF. Those 3 sodiums will be released, and in order to reset the protein, or reset the carrier protein, 2 potassium ions can bind from the ECF. They bind to affinity sites meant for them, and that will cause the phosphate to be released, and the protein will again return to being open on the inside, and we release that. So we're moving, with every time we use our sodium-potassium pump, we move 3 sodium out of the cell, 2 potassium into the cell, and we utilize 1 ATP. Now, a secondary active transporter, an example would be the sodium glucose secondary active transporter, the SGLT protein. Okay, in this case, we're using sodium's gradient that's high outside of the cell, low inside the cell, and so we want to move sodium. We use that concentration gradient. Sodium binds, and we also bind glucose when glucose is at a low concentration outside of the cell. And when we bind, it can then glucose hitchhikes on sodium's high concentration, and they both get moved into the cell. What are some differences between GLUT and SGLT? Well, the biggest difference here is now we're moving glucose from low into high. If we do this, why do we need both? Well, where we tend to find SGLT transporters are in the basal membrane of the lumen of our intestine, right? So here's the space inside the intestine where we're breaking down our food. As we eat a meal, we would expect to have really high glucose concentrations. Those glucose concentrations then move into, say, a GLUT4 transporter and get brought into the cells that make up the intestinal wall, right? Now, just like when we looked at the GLUT transporters, at some point we're going to hit our equilibrium. And in order to keep bringing glucose in, we have to reduce the glucose that we find. And one way we can do that is by offloading the glucose on the other side of the membrane into the bloodstream, which does occur. We could also utilize that glucose inside the cell, but we really don't need that much glucose inside an intestinal cell. It needs a little bit for energy, but not that much, so we don't want to store glycogen there. So in order to maximize, we want to get all of the glucose out. We don't want this glucose to just sit in the intestine and ultimately be lost in excretion. So we have SGLT transporters that ensure that all of the glucose gets moved into this region, and now we're at a high concentration, low concentration in the blood, and it can be shuttled out and distributed throughout the body. So this transporter, secondary active transport, and it would be symport, right? Because we're taking two or more molecules and we're moving them in the same direction. These tables from your book, table 5.7, 5.8, okay, they kind of talk about this. There's other transporters. This semester we'll talk about the calcium ATPase, the hydrogen ATPase, or the proton pump. There's a hydrogen potassium ATPase. They kind of again show you though that you have antiport, uniport. I'm only going to test you over those three that I talked about today. Last thing we should talk about, well, moving with this concept of carrier-mediated transport proteins, we need to talk about how there is specificity, competition, and saturation that occurs. What specificity means is that each of these carrier proteins really only moves one molecule or molecule group across it. Only, a GLUT transporter is only able to bind 6 carbon sugars. Other molecules can't bind into that GLUT transporter. So that's the specificity of the transporter. Competition talks about now when we have substrates that compete with each other for binding sites. So in the case of our GLUT transporters, maltose is a 6 carbon sugar, and it's a competitive inhibitor because the body really doesn't like to use maltose all that much. It doesn't break it down. It's not nearly as effective at getting glycogen. We'd rather bring glucose in. And so these will, maltose will compete for binding sites in these proteins, and it'll slow down the ability of us to bring glucose in. The transportation rate is going to be lowered. You see that right here in this one, right? They're not using maltose here, they're using galactose. But if you have both glucose and galactose, you see our glucose transportation rate is less than if we just had glucose. And finally, we have what's known as a saturation. At some point, we're going to have so much glucose present that all of our transport molecules will be utilized. And it doesn't matter if we bring in more glucose, we're not going to be able to transport anymore. So we'd expect this to go up, and then it hits a concentration saturation point in which it doesn't matter if we put in more glucose, we're going to only be able to transport that amount. That's the transport maximum. Other ways that we can bring molecules into our cells. We can use what's known as vesicle transport. Really all I want you to know on these is what these terms are. So phagocytosis is when you have a cell it actually swallows in and on itself a molecule, and that there can be two processes in which this kind of happens. We can have what's known as endocytosis and exocytosis. Endocytosis is when we bring large molecules into the cell. So the membrane, it basically wraps around the molecule inside the cell. The membrane fuses with itself, and now the molecules found within the cell. That's endo. Exo would be the opposite, in which we're removing. So something inside the cell moves up to the membrane. The membrane then buds and forms around it, and we move it. Or you have a vesicle inside the cell that fuses to the membrane and then creates a pore as the membrane thins on the opposite side, and that large molecule is moved out. We use vesicle transport for large molecules because these would not fit in carrier-mediated. Other ways we can bring things through, we can use what we call epithelial transport, where like in our intestine, when we're trying to move through the cells that make up the lining of the intestine, we can have what we call transcellular movement, in which we are moving through the actual cell. We did this with glucose, right? We would use perhaps like an SGLT transporter, and then say a GLUT transporter on the other side to move it into the cell, through the cell, and then out. Or we could sometimes move it in which we move in the little gaps between the cells, where we move through what we call gap junctions. This would be paracellular. It's adjacent. And I just talked about this transcellular. In transcellular, usually you're crossing two membranes. One is going to be uphill, the other is going to be downhill. And glucose is a good example of transcellular transport. We'll finish up. So why do we spend so much time in physiology? Why do we have this lecture over membrane dynamics and moving things across membranes? Well, this is incredibly important for physiological functioning, not just so we can bring things into the cell and utilize them that way. Of course, that's important. But these differences between our membrane chemical concentration gradients develops what we call a membrane potential. There is that electrical disequilibrium maintained by our cell membranes. If you remember, the main positive ion, what we call a cation, in the ICF is potassium. The ECF would be sodium. And the main ions that we find that are negatively charged, the anions, in the ECF is going to be chloride, and in the inside the cell is going to be phosphorus. Okay, these are not equal to each other, and so we have this electrical disequilibrium that we refer to as resting membrane potential. So the difference between that chemical gradient between the ICF and ECF when in a normal cellular functioning is what we refer to as resting membrane potential. And generally, the ICF is going to be more negative and the ECF is going to be more positive. Okay? So, we have a resting membrane potential that is largely negative. Most cells in the human body, they're going to be much more permeable to potassium leaving the cell than they are to sodium coming into the cell. It's about 40 times more permeable. And because of that, because of this disequilibrium, resting membrane potential in most cells is around negative 70 millivolts. That's what the ICF is, negative 70 millivolts. So it'll be really important when we talk about nervous signaling, which is what we're going to be moving into in the next